You type one line of code to fetch data from a server. To your computer's processor, executing that command takes almost zero time. But before a single piece of your actual data leaves your machine, you hit an invisible wall of waiting. That wait comes from the network layer, specifically a process called the three-way handshake. Before two computers can exchange data, they have to perfectly synchronize with each other. They have to agree on exactly how they will track the conversation. This animation shows how that synchronization works. Your computer, the client, sends a message called a SYN, basically saying, "I want to connect." The server receives it and replies with a SYN ACK. "I acknowledge your request and I want to connect too." Finally, your computer sends an ACK, acknowledging the server's reply. The time it takes a message to travel to the server and back is called the round trip time. Notice that your computer has to wait for one entire round trip across the network before it is allowed to send its very first byte of actual data. For the destination server, it takes even longer. Because it has to wait for that third and final acknowledgement from your computer, the server doesn't receive your actual request until 1.5 trips across the network are complete. Every time you open a new connection, you pay this time penalty. That handshake turns a simple request into a multi-step negotiation, where your data is held back until both machines are perfectly in sync. Once the handshake finishes, the connection is officially open, but the network protocol still doesn't trust you. Instead of letting you send all your data at once, it assumes the network might be fragile and heavily restricts your first burst of traffic. To manage this, TCP uses a congestion window. Think of it as an allowance, the total amount of data allowed out on the wire before you have to stop and wait for a receipt confirming it arrived safely. Because the protocol doesn't know how much traffic the physical network can handle, it uses a mechanism called slow start. It drips a small amount of data into the connection to test the waters, making sure it doesn't cause a traffic jam. Your computer starts sending about 10 segments. When the server confirms they arrived, your window doubles to 20, then 40. Even with blazing fast internet, this limit holds you back. It takes 3 to 4 round trips to finally use the full network pipe. The resource costs don't disappear when you finish sending your data. Closing a connection doesn't instantly free up the memory and ports your computer used. When you close the connection, it enters a mandatory state called time wait. Think of this as a 2-minute waiting period, where the closed connection lingering in the background, staying open just in case any lost or delayed pieces of data arrive late. This animation shows what happens when a busy server opens and closes connections too quickly. Every active connection requires a unique communication port. Because closed connections sit in that 2-minute purgatory, a high volume of traffic will rapidly consume all your available ports. You watch the counter tick up toward its limit of around 28,000, and once it hits the ceiling, your server physically cannot make any new requests. If you treat these connections as disposable items that you throw away after one use, you quickly build a graveyard of dead ports. Eventually, you run out of space and your service crashes. This animation compares two approaches. On the left, a new connection suffers through the handshake and slow start. On the right, connection pooling holds an established connection open, instantly filling the pipe. To see how this saves systems from crashing, we can look at how modern programming languages handle these rules. In the Go programming language, the tool used to fetch web data has a built-in connection pool. This code snippet shows a setting called max idle connections per host. It controls how many open connections the pool will keep warm. It ships with a default limit of just 2, meaning any traffic spike forces your system to open fresh connections, paying the wait penalty repeatedly. Engineers often have to bump this number up to 50 or more to handle real-world traffic. You can see this in your monitoring tools. While your CPU is idle and the target server looks fine, you'll see a sharp rise in the time your requests spend simply waiting to grab a connection from the pool. Reusing connections is a strict requirement for a stable system. Without it, the hidden costs of network negotiation will overwhelm your service when traffic scales. This exact scenario is why senior engineering interviews focus so heavily on the true cost of making a network request. Understanding these invisible barriers separates systems that work from systems that fail under pressure. Engineers have to carefully weigh their options. Make the connection pool large and you eliminate the wait time, but you consume valuable memory keeping all those connections warm. Make it too small, and the constant handshakes slow everything down to a crawl. Newer protocols change the rules. HTTP2 sends hundreds of requests over a single established connection, so you pay the handshake tax just once. Quick goes further, combining the connection and security steps into one, which allows data to move on the very first trip across the network. You have to grasp the invisible tax of a standard connection to understand why network architecture looks the way it does today. And while we just covered the baseline wait time, securing that connection adds another intense layer of negotiation. We'll explore exactly how that security layer works in our next video on TLS 1.3.